Hi, I'm Paul Blanton, President of VEC. Today I'm going to talk to you a little bit about mitigating both DC and AC magnetic fields for transmission electron microscopes or any instrument with a long electron beam column. So these instruments are challenging for mitigating both DC and AC fields for three reasons. The first is the specifications are often very tight, kind of 20 nanotesla, 30 nanotesla peak to peak, which is very difficult to achieve. The second is the electron beam column is very long. So unlike a SEM, which has or scanning electron microscope, which has an electron beam column of only a couple feet, a transmission electron microscope can have a column length of a couple meters. And then the third reason is there's multiple points along the electron beam column that require this very tight specification. So oftentimes there's 3 points of measurement: the source at the sample height, and then at the detector at the bottom. And because the specification is so tight and the points that require the very tight specification are far apart, a couple meters apart, achieving that tight specification is often very challenging. So we've done a previous video about how magnetic field cancellation systems work, and we'll provide a link for that video in the description below. But there's primarily two factors that impact how effective a magnetic field cancellation system is. One is the cable layout. That is used to determine both the magnitude of the magnetic field that can be canceled and the uniformity of the field cancellation. And the second is sensor placement. Because the magnetic field cancellation system is optimized for sensor location, or sometimes the weighted average of 2 sensor locations, the sensor placement basically determines the point in which the field cancellation system optimizes for, and is critical when it comes to the impact of the system on overall magnetic field cancellation and system performance. So we've talked about the 3 reasons why it's challenging to mitigate both DC and AC magnetic fields for transmission electron microscopes. And it's particularly apparent when it comes to field gradient. Imagine you're in a situation where you have a TEM lab with an overhead electrical conduit, and you have 100 nanotesla of field at the source level, 50 nanotesla field at the sample height, and 20 nanotesla fields at the detector level. Typically with a dual cancellation system, a single dual loop cancellation system, VEC will optimize the field cancellation system at the center of the microscope and try to provide uniform cancellation along the electron beam column. And so the result is, if we've optimized the field cancellation system for the center, we have under canceled by 50 nanotesla at the top and over canceled by 30 nanotesla at the bottom. And if the spec is 20 nanotesla peak to peak, we basically are out of spec at both the source and the detector level, which is problematic. So because of the challenges of mitigating both DC and AC magnetic fields for TEM labs, one option to explore is shielding. There's really 2 types of shielding. There's AC shielding, which is typically eddy current shielding using typically 1/4 inch C-molded aluminum. The second is flux shunting, which is for DC and AC fields, and that uses either mu metal or a silicon iron alloy. The way eddy current shielding works is basically the AC magnetic fields induce eddy currents in the aluminum, which then generate a induced field which cancels the magnetic fields and prevents them from entering the room. The second type of shielding, the flux shunting, uses the highly permeable material like mu metal. Basically, it creates an envelope around the lab that the magnetic fields then follow and do not enter the lab. So because the shielding is a highly permeable material, the magnetic field lines basically follow the permeability of the material shielding the labs and do not enter the labs and do not interfere with the microscope performance. Shielding does work and provides either AC shielding or DC and AC shielding, but there are some drawbacks when it comes to shielding. One is, if you do eddy current shielding, aluminum shield your lab, you really only protect yourself against AC magnetic fields. So, the tight specifications for the microscopes, so say 20 nanotesla peak to peak. Yes, you might shield the AC component of it with aluminum, but you're still going to need to mitigate the DC component from trains, elevators, or activity around the laboratory. Well, why don't we explore both DC and AC shielding? Why don't we use mu metal shielding? Well, that works and certainly is an option. However, it is very expensive, and the lead times for these materials are often years. And so, although it is an effective way to shield your laboratory, it's often timeline and cost prohibitive for many customers. So another option to, in lieu of shielding or in conjunction with AC magnetic field shielding, is a dual cancellation system. And so a dual cancellation system solves the problem of field gradients on transmission electron microscopes. Basically, the way it works is you have two independent field cancellation systems that optimize for two different portions of the microscope. You have a top system that optimizes for the top of the electron beam column, typically with the sensors optimized with the sensor optimization point near the source or somewhere between the source and the sample height. And the second is at the bottom half of the electron beam column with the sensors optimized for the detector location. So let's talk about how a dual cancellation system plays out in our previous example of an overhead electrical conduit. Because you have two systems, one optimized at the top near the source, one optimized at the bottom near the detectors, the field cancellation system at the top cancels that 100 nanotesla field experienced at the source, resulting in a field level at or near zero. At the same time, you have the field cancellation system at the bottom, which is detecting that lower field level of 20 nanotesla, and it's optimizing for the detector location, and so the field cancellation is at or near zero at the detector. And so you basically have two optimization points with a smooth transition between top to bottom of the microscope, allowing the entire length of the electron beam column to be within that very tight 20 nanotesla peak to peak specification. So with VEC, in addition to being able to use a dual cancellation system to optimize two systems, one for the top and one for the bottom of the microscope, we use what we call a virtual sensor, using two individual sensors to create an optimization point inside the electron beam column. Because the field cancellation system's optimized for the sensor location, if you have one sensor and that sensor is not inside the electron beam column, the optimization point for the system isn't really where it matters the most because it's not at the electron beam. But if you use two sensors, basically you put one on either side of the column, and you take a mixing of the signals and you create a weighted average in the center of the column, and it allows you to create a virtual sensor at the electron beam inside the column of the microscope where cancellation matters the most. Although dual cancellation systems aren't the only way to mitigate against field gradients, it is the best way to mitigate against field gradients. One way our competitors, we've seen them mitigate field gradients, is by what we call hardwiring and a gradient into the field cancellation system. And so imagine again you had a higher magnetic field at the top of the room than the bottom. You could create a field gradient by having more cancellation loops at the top of the lab versus the bottom. The problem is you've basically hardwired a static gradient into your laboratory, and it's not dynamic. So imagine you have electrical conduits above your lab, you have your kind of persistently handling that field gradient, but then you had an intermediate source of, say, DC fields coming from a train below your lab. And so because the field gradient is hardwired into the system, you cannot handle the different gradients from different directions. And so although you'll be fine mitigating the kind of consistent AC fields from the electrical conduit overhead, you will not be able to handle the field gradients from the DC fields coming from the terrain underneath. So another approach that we see with customers with both DC and AC field issues for high-resolution TEM labs is the integration of a dual cancellation system with eddy current passive shielding for AC field. Many customers like the permanency that AC eddy current shielding provides, but remember the DC field sensitivity of these instruments is extremely high, and it doesn't take much for the specification to be breached. And so we often see customers use aluminum AC shielding to mitigate the AC component of the magnetic fields, and then a dual cancellation system to mitigate the DC component of the magnetic fields, providing both DC and AC shielding for the TEM. So I hope this video was helpful for you to understand both the challenges and strategies for mitigating both DC and AC magnetic fields. If you have any questions about the material in this video, or would like to learn more about DC and AC magnetic field shielding, don't hesitate to reach out to us at www.vibeng.com or give us a call. Thanks, and we look forward to hearing from you.